Hello, everyone. Thank you very much for nice welcoming. Thank you, Oleg. Thank you, Dmitry. And thank you to the whole JAC crew group for amazing organization of the event. That's the best I've ever seen. And this is my first virtual conference. So I'm a bit nervous because I can't move. I don't have a standing desk. I will have to be tied to my chair, but hopefully I will not screw up that badly. A little bit about me. I will also need to get used that the slides will come with a short delay. So about me, I'm currently working at Hazelcast and not as the quality engineering team lead anymore, but as a product manager. And hopefully most of you guys just didn't left at this point because I know how engineers like product managers. And I switched the role approximately 2 months ago, so this is very new for me. But before that, I was a quality engineering team lead at Hazelcast, and even before that, I worked in Red Hat as a quality engineer as well. So really, I'm more like an engineer. Hopefully, I will prove myself to be an engineer today, not a product manager. And one thing to also note is that I'm not Intel advocate. I'm not trying to sell the Intel Optane here or try to claim how great it is or how bad it is. I would like to share our experience with Intel Optane DC when we were implementing the stuff, the support at Hazelcast. So let's go. Let's talk about Hazelcast a bit, or why is this relevant for Hazelcast? So as you might know, Hazelcast in Hazelcast we do in-memory computing platform, basically mostly known for the distributed feature-rich distributed cache. And besides that, we also do stream processing engine called Hazelcast Jet, and both of these things as a managed service in Hazelcast Cloud. So these are the offerings. I would be actually very curious about how many of you have ever heard of Hazelcast or is using Hazelcast. So Oleg hopefully shares the poll in the Telegram chat. So please vote there. It's for my curiosity. And at Hazelcast, all we care about is performance, because who would use a slow cache? Who would use a slow stream processing engine? We are doing the stuff in memory to be fast. So all we care about is performance and in-memory technologies. And that's why we're going to talk about Intel Optane today. Intel Optane today, because it's from our point of view, it's interesting technology or promising technology. Let me go through the next slide, and that would be a motivational demo, or to show you something. What are we going to talk about during this presentation? Let me share a benchmark. I prepared a Jma benchmark for you to compare something. At this point, I will explain what the benchmark does. For those of you who are not familiar with JMH, don't worry. Long story short, this is a benchmark that measures how long it takes to do stuff. And we have what we do here. We will create a byte buffer of size 4 kilobytes. We clear it, then we fill it, and then we write it to the underlying storage. And these operations we will perform on 2 underlying storages. One of them will be like a regular SSD disk, even though I'll be running this benchmark on our private performance lab at Hazelcast. We have pretty beefy boxes there, and so the SSDs there are really fast, also really fast. but we will also run it on the Intel Optane non-volatile memory persistent memory module, and we'll see what the results are. We will to compare it. Let me try running the Jma benchmark itself. You should see my console at this point, and I'm running the iterations. I'm running the benchmark itself. It should not take more than a couple of seconds, and here we have the results. So in order to interpret the results, you can see that the case with non-volatile memory, the Intel Optane back one, is like, what is it, like 150 times faster, orders of magnitude faster than the regular SSDs. And this is the thing that caught our interest. And this is something that would be worth exploring. And that's why we're here talking about Intel Optane today. Hopefully, I still got your attention that this is pretty fast. This is a pretty nice storage or worth investigating. So let's look through the agenda, what we're going to do in this talk. I'm going to introduce a bit the Intel Optane, what it is, because it's the marketing and the branding is a bit confusing. So I will try to put some sense into it. We'll talk about use cases where Intel Optane is better or worth looking at, and where it could shine. Then I would like to show a demo how you can work with Intel Optane and Intel Optane through Java, through the new APIs in JDK 14, and also show you the example how you have to do it before JDK 14, which is, as a spoiler, not that nice. And in the end, we'll discuss the pros and cons, and maybe put some other details about Intel Optane. So I'm still using Intel Optane DC. So what is Intel Optane DC? It's a brand. It's a brand, but we'll be talking about, or I'll be talking about Intel Optane DC persistent memory module. And as the name suggests, the memory module, it's a DIMM module. It goes to the DIMM slot. It sits on the memory bus, thus very, very close to CPUs. So probably it will be very fast, hopefully, and is orders of magnitude faster than SSDs, and is also persistent as opposed to the DRAM, to the regular DRAM. You saw in the motivational demo that it's apparently very, very fast. At this point, you might think, hey, I've heard of something called Intel Optane, but that went to the PCI Express slot. That but you're talking about DIMM slot. What is this thing? That's another name, that's another product basically. So it's Intel Optane is the marketing name for the technology, and there is Intel Optane persistent memory module, and then there is Intel Optane SSD. So Intel Optane SSD is basically making or faster SSDs. Very shortly put, and you can see the picture of what it really looks like. So it's a card. In order to put this into a bigger perspective, so let me show you a nice Intel Optane marketing diagram. What they present is that for the fastest storage, they use the DRAM, the hot tier, the fastest storage. Then we can use the Intel Optane DC persistent memory module, which should be slower than DRAM, but faster than SSD, much faster. And then there is this Intel Optane DC solid state drive, which is like above the regular SSDs. So from now on, I will be talking about the Intel Optane DC persistent memory module only, because this is the newest, the coolest, the hottest stuff that Intel is producing. And this was the choice that we made in Hazelcast because the SSDs are still very slow for us, even the Optane SSDs. That's not good for our in-memory use cases. So the Intel Optane DC persistent memory module, this is going to be a hard time repeating it all the time. So we tried with that. So once again, what is it? So it's a byte addressable storage, just like DRAM. It's persistent, just like disks, SSDs. However, it's much faster than SSDs, but just a bit, let's say, a bit slower than DRAM, and is half of the price of DRAM for the same capacity. So it offers a nice compromise between the costs and the speed. On the table on the right, you can see the memory bandwidths, the parameters from the from Intel or from some kind of shop, and you might argue that the sequential writes of some SSDs are 3.5 gigabytes. So what am I talking about that this is faster? You have to keep in mind that this is per DIMM per module bandwidth. So if you put multiple DIMMs in the server, the throughput will scale out. So this, and it will kick SSDs as pretty hard. So that's a promising thing to look at. And let's see how we could leverage Intel Optane DC persistent memory module in real use cases. Sorry. So the three main use cases that we were looking at was first the cheap DRAM. As I mentioned, Intel Optane DC persistent memory module. From now on, I will be just using Intel Optane. Sorry, I need the shortcut. Is half the price of DRAM. So imagine you have a very memory demanding application. I could say like a database server, for instance, and you have a very large data sets that you want to fit into memory because you want to operate with them as fast as possible, but you don't actually have the money to buy like that much memory, that much DRAM. So you're looking for a compromise. One of the compromises might be actually Intel Optane DC persistent memory module, because as you see from the slide, it's less than half the price for some modules. So you can enlarge your server's memory capacity by far for keeping the reasonable costs. And that's something that for our customers at Hazelcast, they are looking into it very interestingly, because they have big boxes with terabytes of memory, and that would cost a fortune. So some of the customers are actually looking for this, let's say, easy use case. The next one that I actually demonstrated during the motivational demo is that we could use it as a super fast storage. We could use it as a super fast SSD, and as a super fast SSD. For instance, for a Hazelcast, the use case that we are looking into is that whenever our server comes down, you need to restart it, and we want to have as short a downtime as possible. So the possibility is that we can store the data at Hazelcast in the Intel Optane, and when we restart the server, it will read it into the memory much faster than from the disk. So making it in order to make it more fault tolerant, easy to restart, for fault tolerant use cases. And that's another use case that is interesting for us. Just imagine that you need to query a lot of data that you have stored on the disk, and you can't fit it into a memory. You just can't do it. So that's where the Intel Optane will drastically increase performance of your application, because it's much faster than the SSDs. One of the more advanced use case would be so-called tier storage that we're also looking into right now. This use case is aiming to use your storage capacity is as efficient way as possible. So you store the data based on their type or the frequency that you use or the use case that you do with them in the corresponding storage. Like, for example, you use the hottest data in DRAM. So, for instance, for a Java program, in case of Hazelcast as well, that would be the heap. You know, you want to have the heap on the fastest storage as possible to not suffer, for instance, for the garbage collection issues, pauses and stuff like that. But then you can store the data that are not accessed that frequently into the, but still pretty frequently in the faster storage, for instance, SSD, Intel Optane persistent memory module. And then for instance, for archiving purposes, you can store the rest of the data, the large capacities, on the slow disk, on the tapes. And when we were in college, everybody said tapes, but I don't know if anybody works with them that much. We don't at Hazelcast because we try to keep it in memory the opposite way. So these are the use cases that we might find Intel Optane persistent memory module helping us nicely with. And now let's look at how it works how it looks like in practice. So how do we implement the use cases? What can we do to make use of Intel Optane persistent memory module in Java? And here it's where it gets a bit ugly, because all the primary libraries, all the first class citizens, first class support for the non-volatile memories is written in C. And for us as Java developers, this is problematic, because how do we access the C code and how do we access it efficiently? However, there are ways how to leverage Intel Optane DC even nowadays with all the JDKs and on Java. And this is how we did it in Hazelcast. As mentioned about the libraries written in C, there are plenty of them. There are like 10 or 12, I think. You can find the whole list on the PMDK, Persistent Memory Development Kit website. And there are libraries that are good for persistent use case, and then there are libraries that allow you to do advanced in-memory stuff, volatile stuff, and stuff like that. But that's going really deep into the C libraries code. So let's see how we can do it in Java. For the first use case, okay, I really need to switch the slides a bit earlier. For the first use case, as using as a cheap RAM, you're basically not leveraging the persistency of Intel Optane. You're not leveraging the magic there. But it's still a very valid use case. And in our case, some of our customers are looking into that use case as well. The options that you have with Intel Optane DC, persistent memory module, is that you can either configure its so-called memory mode, which means that you put the Intel Optane DIMMs enlarging the memory, and then the regular DRAM actually serves as level 4 cache for the Optane persistent memory. So for some workloads, you can achieve increase of the memory capacity, but still keeping the RAM-like speed and for reasonable costs. The other one, there are more of them, but the other most important one would be that you actually want to add. You don't want to hide the DRAM behind the persistent memory modules, but you can add it to the existing DRAM. So for that, you have to configure the Intel Optane PMMs in so-called app direct mode, which means that the application has to know about it. The application has to think about where it allocates the data from, and it's not transparent anymore to the user. To the user. So you actually, as a developer, you have to take this into account. At least the first use case, the memory mode, is completely transparent to the developer. So you don't have to do anything for your application to make use of this big persistent memory capacity. So as I said, maybe from the developer point of view, this case is not that interesting, but from the customer point of view, that's still something worth investigating. Another use case that I mentioned is that we can use Intel Optane persistent memory modules as a super fast persistent storage. So for our use case as a fault tolerance, the data will remain in the memory, and we can get to manipulate with them reads and writes very, very fast. And how do we do that in Java? In JDK 14, which was released, I think, like 2-3 months ago, this is surprisingly easy. The support for that is there finally, and we will show a demo in the next minutes how you can do it there. However, on the older JDKs, there is no direct support for in Java for the non-volatile memory awareness. So you will have to go through the pain of interacting directly with the C libraries and through JNI calls. It sounds horrible. It's not that horrible, but there are some pain points, and we will discuss them later on. For the last use case that I described as a tier storage, the options are pretty much the same. That for the JDKs 14, there is the new API or direct support, so you can actually choose where you allocate the data from. And for all the JDKs, again, you have to go from the combination of C libraries and JNI calls. So it's cumbersome a bit. I don't know how many of your users and customers are on JDK 14. For us, it's a very, very minority. So we actually had to go through the support of C libraries and JNI calls. So let's take a look at the newest, hottest stuff in JDK 14. Coincidentally, I learned that Dmitry was actually doing a review of the JEP for that. So hopefully he will not crash my my thoughts in here. So let me show you a code that you can use. You can use to access it via byte buffers. The access in JDK 14 is pretty straightforward. So as usual, you could use byte buffers, which is the standard way if you want to squeeze the most of the memory out of most of the performance out of the system. And this is how the regular let's say memory mapped files work. So you take a file with a path, then you get a channel out of it, and then you map the file into the memory, into the byte buffer, and you manipulate on the memory. What's the most convenient part on JDK 14 is that the only change in order to support, to distinguish between the persistent memory and the regular file system or regular mapping mode is that you only need to change the map mode enum, the map mode param, from read-write to read-write sync. And from this, the JDK understands, hey, he's trying to use the non-volatile memory. Let's check that he's pointing to the non-volatile memory. And if you're not, the JDK will alarm you. It will throw unsupported operation exception, which is pretty nice. And it will leverage the performance of Intel of the non-volatile memory modules. It will do it more efficiently because when you're writing to disk, it's you're doing the file flushes. You have to do a syscall, which is pretty expensive. But with the non-volatile memory that is byte addressable, you don't have to do that. So you're flushing directly the cache lines, which is much faster. And JDK 14 and later are aware of this fact. So that gives another boost in performance. So JDK 14 level support is very sweet. It looks very nicely. Good job, Dimitri, with the review. But as I said, at this point, and I guess for a couple of years, we will not be meeting that many customers with JDK 14. So how can you do the stuff with older JDKs? And now we're going to the kind of messy JNI calls and interaction with the C library. So I've written a very short, as trivial demo as possible. For those who are not familiar with JNI, that's not a problem. Hopefully you will understand it as well. So this is basically the basic principle is that you do a regular JNI. You have to write your own C code, doing the allocations, interacting with the persistent memory libraries, and then you take it through the JNI. You connect these two pieces together and operate in Java over it. So you load the C libraries. You load the C libraries into the Java ecosystem. At this point, and as a next step, you init the memory, the persistent memory, through by calling this native method init0. We will look at the implementation afterwards. And for example, I'm initiating as a pmem kind. We are using the C library named memkind, but as I said, there are plenty of them. I just chose that one because it fit my purpose, and we are using it at Hazelcast for the big thing. And once you initiated the memory, you said, hey, I'm going to use that. You can really allocate. You get the pointer in the memory with the size of, let's say, 5 bytes. So actually allocating, you get the pointer, and then with the pointer, you treat it as usual or as usual business with unsafe, where you actually have raw access to the device. You have to. There are no boundary checks. It's all on you, so you have to be quite careful. Hence the name unsafe. But it's not that horrible. And for everybody who ever implemented something on OVHIP, the unsafe is your friend, really. And let's take a look what the alloc method looks like. So as I stated, it's a native call. It's a native method that points to a C code. So let's take a look at the C code. The C code is very trivial. Let's wait for the slides to show up. But the C code is very trivial, that I'm actually calling. This is the call of the C library, the non-volatile memory library that is provided, I think, from guys from Intel as well. This is allocating directly on the Optane DC memory module. So this is how you put the pieces together. This is what you have to go through, and obviously you have to go through the regular JNI ceremony, which is GC, which is compiling the code, then linking the code, then putting a path to the code to your Java program. So there is some ceremony, but it's not that horrible. But unfortunately, this is the only way that you can make your Java program persistent, memory aware, or make the best use of it. If you're on older JDKs. There are also other things that are worth noting regarding Optane, but there's so many things. You can go so deep into the details because there are so many modes of the memory that you can configure, like a direct access mode, and then like the KMem mode, and the memory mode, and app direct mode, and file system mode. So this takes a lot of time. One thing that I would like to mention is that there's, for instance, this PCJ persistence collection for Java library that is available from the PMDK developers. The library provides like the non-volatile memory aware implementations of array lists or hash maps or queues. So it would be very useful to, it would be nice to use it. But unfortunately, the repo is still, they claim it in the README, it's in the pilot mode, and there hasn't been a single commit in a year. So that looks a bit like abandoned library. But luckily, the guys from JDK, OpenJDK team are picking things up and providing the out-of-the-box support for non-volatile memory. There are also some limitations that you need the high-end Xeon Platinum series CPU in order to support the Intel Optane persistent memory modules, because there are some instructions that that can leverage the PMMs. And these CPUs are not that cheap, but they are also very, very powerful. And there are other things that we learned during development of our support for Intel Optane in Hazelcast. So one of the biggest takeaways was that we really should invest time. We have to invest time in the NUMA awareness for maximal performance, because that's what we care about in Hazelcast. The DIMMs, the other caveat or thing that you have to keep in mind is that the DIMMs are mounted based on the socket that are assigned to. So let's say, and as a mount point, you will get the mount point PMM0, and these are the DIMMs that are mounted to the socket number 0. And then there are, like, other 4 DIMMs are assigned to the socket number 1 and then number 2. So if you want to use the big chunk, the whole Optane memory, you will actually have to kind of like switch between mount points, which is not the one big continuous block of memory, which was a weird realization after a while. One interesting interesting scenario that I was talking about was that the NUMA awareness affects performance a lot. By NUMA awareness, non-uniform memory access, that means that the Optane memories, the memory is assigned to the CPU, that and the reads from this memory from that CPU are very fast. But if you want to read from a memory that is assigned to another CPU, you have to go the long road, and there is a performance penalty. And from our benchmarks, we saw that the performance penalty is hitting Optane memory pretty hard. So we invested a lot of time to make sure our implementation is NUMA aware. Therefore, the CPUs, the threads running on the CPU, would read or store operate with the Optane memory assigned to the CPU, thus avoiding remote access, thus avoiding the performance penalty. So let's start with with conclusions and then lessons learned at our side. So when is Intel Optane persistent memory modules for you? If you need the top level performance, if you care about microseconds, then you're probably working a lot with the memory. And there you need also a lot of the memory. So that's one case where persistent Optane is worth looking at. If you're working with files and you need to work with them in a performant way, and big files maybe, you can use it as a very fast storage, another case. And if you don't have that much money, but you need to get a lot of RAM or a lot of fast storage, also there is something, these are the cases that Optane persistent memory modules should be taken into account, and you should take a look at that. About the conclusion of what's the state of the persistent memory modules and Java. So in the JDK 14, the support is pretty sweet. It's very simple, just regular byte buffers, regular memory mapping files, just with difference of one enum change. So that's pretty sweet. But with all the JDKs, you have to go. You must not be afraid of the JNI and unsafe and some manual work. We implemented quite a big code base on it, and it wasn't that big of a deal, but it is some pain point. So we're very much looking forward to JDK 14 when it becomes a standard, and we can use the capabilities provided by the JDKs. And there are also other enhancements that are coming regarding non-volatile memory. So that's pretty sweet that it's getting traction from OpenJDK developers as well. As a conclusion, what I would like you to take from this talk is that the Optane persistent memory module technology is promising. It shows amazing results. The Java support is better in the recent versions, and but for although it's a bit clumsy, but still very usable, and you can do some real magic stuff or really useful stuff in terms of performance gains for certain workloads even now. And one thing is that you can try it out in Google Cloud. Actually, Intel and Google have a partnership where they claim that they will offer Optane in the cloud. And the thing is that I haven't actually tried it myself, because you have to fill a form and provide details. It's not like you just click run instance and choose an Optane type. But still, it's something that is available for the public. With that being said, I believe I'm done with the presentation. I'm at the end. Hopefully, there will be some questions, and I'm not a complete embarrassment. So thank you very much for listening. Hope you enjoyed it, and now I'm happy to discuss with you further and answer your questions.
Oh, okay. Let's read our chat. Dmitry is asking, could you tell more about using Obtain DC as a Web4 cache?
Okay, so cool. So that's a, let's say, so-called when you install the persistent memory modules into the system, you actually have choices how to configure it. There are several modes, and one of them is so-called memory mode, and that means that the total capacity of your memory, of your system memory, will be equal to the amount of Optane PMM capacity having DRAM serving as a level 4 cache, like even between the CPU and the Optane memory. So for certain workloads, you will get almost or very close performance capabilities as DRAM, but with higher capacities. Because, for instance, the smallest persistent memory module that I found on the internet is 128 gigabytes. That's the smallest one, and as I said, it costs like half the price of the DRAM. So you can actually enlarge your memory capacity quite significantly with reasonable cost. And for some workloads, keeping the performance benefits of DRAM, let's say DRAM-like speed. It's in the same ballpark. It's not orders of magnitude slower. It's like, let's say, 6-7 times maybe. Hopefully that answered the question. Hopefully.
Okay. What about legacy applications? Like, what is an upgrade path for like corporate users? Is there any magic DLL or shared libraries that automatically make your legacy apps NVMe aware? Oh, I think persistent memory aware.
So I see. So that depends very much on the use case that you want to use. If you're going to use the memory mode that I just described, you don't have to do anything to your application. This is completely transparent to the application. This is all OS level configuration. So that's one thing when you can leverage it. But you're actually using it like a cheap RAM. You're not utilizing the persistent feature. If you want to use the persistent feature, you will have to make changes in your application code. Your application has to be aware. It has to use the libraries. It has to get the support for the non-volatile memory. So yeah, to sum up, if you want to use persistent and it's a legacy application, you want to store your critical data in a fast storage that would be fault tolerant when power goes off, you will have to do changes to your application. It's not like you can magically migrate it to the new persistent memory world and the sun will shine still the same. No, that's not the case.
Maybe we can write a loader that will replace a part of loading configuration or something outside of your legacy app, because some legacy app have no source code; they are lost. Okay.
Sorry, would you mind repeating the question? I got lost a bit. Sorry.
I think I was too. So let's continue. Did I understand correctly that now you absolutely need Xeon Platinum to use Optane?
Sorry, what was the end?
Did I understand correctly that now you absolutely need Xeon Platinum processors to use this technology?
As far as I know, and hopefully this hasn't changed since last month, yes, the support for Optane memory is only in the Xeon Platinum series of the CPUs. There are instructions supporting the PMMs. So hopefully, and like 99% I'm sure, but hopefully I'm still right that you need to have the Platinum series Xeons on the server. So obviously it's not that affordable or not really the main use case is obviously not like on the desktop.
Is there any plans from Intel or any other company to use NVM that is affordable to major audience?
You mean like other? You mean to get the Optane?
Yeah.
Oh, to the desktop users. So
users, yeah.
I see. Not that I know of. I haven't seen any public releases that they would be making some kind of cheaper way of providing persistent memory modules. I haven't heard of that. I'm not saying it's not going to happen, but I'm not a Intel employee, so I really don't know what the plans are.
So Dmitry is asking, are there any other vendor options in some cloud? Does Google plan to make Optane DC a regular option?
So as far as I know, or as far as I Googled, the other cloud vendors, including AWS, Microsoft Azure, IBM Cloud, also Oracle Cloud, that's the only ones I know. None of them provide or announce any offering, including in Optane persistent memory modules. So if you want to use Intel Optane DC PMMs in the cloud, you will have to go through the Google Cloud. And I didn't have actually I don't have a hands-on experience. I've read their announcements that they are offering it, but I don't know really how it works in practice, because that's not the way. This is not that relevant for Hazelcast, because a lot of our customers are using on-premise, but it will probably become relevant in the future soon, because they are moving. Everybody's moving to cloud, basically.
Okay. Your code on slides was pretty simple. Are there any special operations that are specific for this type of memory? Like everyone knows that for regular SSD we have trim and other crazy hybrid memory operations where we can offload a part of SSD into DRAM, etc. Is there anything like that for persistent memory?
You mean from? Oh, you mean so in the JDK 14 there is no like not that I know of, like specific low-level things that you can tweak and play with, like the very advanced fine-grained approaches. If you want to use but there are a lot of there are actually a lot of tweaks and fine-grained options, but these you can use only through the C native libraries, which you have to call through the Jma that we showed in the demo. So there are like plenty of options that you can specifically set the Optane memory for optimization to use huge pages, or you can use it in the mode that it protects, it has memory protection, access protection for security, or you can configure it that you don't want to protect the memory. You can that some other process might actually read the memory that you're just writing into from other process. So for instance, that would be very useful, or is very useful for backups. In case of Hazelcast, that would be you're spilling the data on the Optane memory, and there is another process that is reading data and maybe uploading it somewhere else, in parallel, so not affecting the performance that much of the application. So this is like many of the use cases. If you want to get really top level performance, squeeze everything that you possibly can out of it, you will have to in our benchmarks it showed that the JNI calls and the low level access is the way if you really want to squeeze everything out of it. But perhaps this will change with more support for non-volatile memories in JDKs, in later JDKs.
Okay, that's a good answer. So Dmitry is asking again, is access latency for Optane DC as stable as for RAM in general?
From our benchmarks, I did just one note. I didn't want to share the specific charts, because these are very specific to our use case. And if you're experienced in performance testing, you know that if you want to do the performance test right, you need to do it. It's every scenario. It's very scenario specific. So in our use cases, we found that the latency of Optane DC is very stable, is close to, it's again close to RAM. It's not RAM-like, but it's close to RAM, orders of magnitude faster than SSDs. And and that's thank you very much for the question. That's one of the things that the NUMA awareness was. The NUMA awareness was the most important part for latency, because if you want to access the data in the memory that does not belong to your CPU, you have to go the long road, the remote access, and then it hurts the latency specifically hurts badly, which was a major pain point for us, as we care about like microseconds. So yes, the technology itself, the latencies and throughputs are, in my opinion, very stable.
Okay. Can a programmer deal with NUMA information at Java and Jna level?
Okay, now we're moving a bit towards the NUMA awareness. So we implemented what we're implementing in the recent version, which is Hazelcast INDG 4.1. You can actually check the code; it's open sourced. And what we implemented there is that you can retrieve the information for the operation threads that processes the operation. It can retrieve the information of on which CPU or which NUMA unit. NUMA, how do we call it? Yeah, NUMA node. Yes, that's the terminology. On which NUMA node the operation is running, and then we based on the information you can based on the information you retrieve where your thread is actually running. You can based on that you decide which memory you will read from or write to, thus avoiding the remote calls. There are ways how to do that. One of the libraries that provides the NUMA like the NUMA control options is Peter Lorry's library. I don't recall the name, but you can get it get from it all the information. The tricky part, which you can't really automatically retrieve, or we haven't found a way how to automatically retrieve, is that how do you get from Java directly which memory modules are assigned to which NUMA node? So in order to support this, because this is essential, right? You find out where you're running on which NUMA node, and based on that, you restrict the memory that you read from or write to. But the mapping itself is not easily, or we haven't found a way how to retrieve this information at all. So how we did it at Hazelcast, because this is a very low level tuning, right? So how we implemented it at Hazelcast is that the user actually has to specify the mapping. So in the configuration, the developer says, or the user of the Hazelcast has to say, hey, these are the CPU NUMA nodes, and to that NUMA nodes, these are the DIMMs or the mount points, to be more specific, the mount points that are assigned to this NUMA node. And based on that, Hazelcast can intelligently access or point itself into the right mount point to provide optimal performance and not suffer from the remote calls through the remote NUMA calls.
Okay. So
I told you, be gentle, Dmitry, with me.
I'm as gentle as possible. Thank you. The topic is very interesting, very hot. So you probably have already users of this support in Hazelcast, right?
that's truth be told, is that the feature is relatively new. It's in the new major version of Hazelcast 4, which was released in February, and our, let's say, main customers, the big ones that really care about that kind of stuff, terabytes of data in memory. These are like the financial, banks and big companies that are conservative in upgrading. So truth be told, so far we don't have like the feedback, or I'm not aware of any feedback from a production environment that this is running to, but we have a few prospects evaluating it in the evaluation phase, and they shared pretty much the same results that we had. That it's actually working pretty well. There are massive performance gains.
So may it be like this is the major scenario, because this memory may be cheaper than RAM, so you can have a lot of space for IMDG, and you just can use it as your main memory for IMDG.
Exactly. I mean, that's why I'm saying that I think the persistent memory itself, because before, the Optane SSDs, they were faster SSDs, but still very slow compared to DRAM. But these persistent memory modules are quite close to DRAM itself. So I anticipate that in a few years' time, we will hear about this technology much more, and that we could actually, say, okay, if you want to achieve this performance SLAs, you will have to get the Optane memory. With that, it's completely possible. So maybe this will become a very relevant scenario for the IMDG.
So, for example, if you currently run Hazelcast, you may specify that use just non-volatile memory for all the cache, and you probably will need some real RAM heap for your operations. Yeah. But how much will be that heap, and how much may be the rest, the non-volatile part, if you put everything there?
Yeah, so at Hazelcast, this is specific to Hazelcast, right? So we choose, you specify in the configuration that you want to use that much heap, and then you want to use of heap. The rest of the data you will use of heap, and for the of heap you use Optane. You use non-volatile memory. And you can specify how much there, where are the mount points, what is the mapping between the nominals, etc., etc. So it's completely up to you how much you want to put there or not.
Interesting. So it's basically, as I said, you can use just put entire useful user information there. Do you have such mode in your integration tests, or it's complicated because of you need Google Cloud or dedicated hardware or something?
We actually we have 3 Optane machines, like with 1.5 terabytes of data in our Hazelcast Performance Lab. Hopefully, I'm not saying anything that is secret. So we can actually do performance tests and do the integration tests on the real hardware, on the real deal, and we do. We have integration tests that because you can detect if the persistent memory is there. You can detect it with the even with the C library. It's a bit tricky, but you can do it. So we if the test is running on the Optane machine, then it will use the Optane for as a backing storage for the of heap memory.
May I ask about how it is working on a hardware level? I still don't understand. So Intel said that 3D exponent memory is 1,000 times faster than regular SSD, but actually it is limited by PCI bus, PCI Explore bus, for example, and it's not so fast. So instead of 1,000 time improvement, you have a very tiny hole in hardware to pass your data. And motherboards are not ready too. Like if you put another 2 PCI SSD in NVMe factor, it always means that you can't use a bunch of SATA ports now, and your hard drive is not working anymore. So is it solved somehow?
So I'm not that familiar with the, or not familiar pretty much at all. I have never tried it. I have no hands-on experience with the Optane SSDs, that go into PCI Express. That I don't have any experience from my own. With the persistent memory modules, I believe like the three main points why it's much faster is first the memory itself, the hardware itself is faster than SSDs. Then it sits on the memory bus, which has the higher bandwidth than the regular SATA interface, like for the regular SSDs. So it has a higher bandwidth. And the third thing is that you don't operate on the software level, or for instance, the Linux kernel is aware of the persistent memory, and when you call, it's not a regular block-sized storage, and since it's byte addressable, it bypasses the syscall. So it detects, hey, this is a persistent memory thing. I don't have to go to kernel to syscall. I will go directly to that memory, which translates into another performance benefit compared to the regular SSDs or regular block storage devices. So these are in my opinion, the three main points where it gives the speed. Also, in case of Optane, in case of the byte addressable memory mapped non-volatile memory, it's writing to a disk. It doesn't have the whole ceremony as I said, the flash to the drive completely, or flash to the drive, or the syscall. It's just flashing the CPU cache lines directly to the memory. So you're just bypassing the long road, gaining extra, giving it the extra speed. But I cannot. Yeah, go on.
Yeah. Please continue.
Yeah, I mean, I probably can't go into like low-level hardware details without big preparation. I mean, I have to. But these are I think I have somehow answered the question. Hopefully.
Yeah. As we go straight to memory, are there any perky error corrections or something? So we probably don't have anything like RAID option for non-volatile memory, but maybe it has some mechanisms to at least try to recover some errors. I don't know, in hardware.
That's on the hardware level, right? The thing is that the Optane persistent memory modules, when you install it into the system, there are like 14, 15, or maybe even more modes how you can install it. I'm not aware of any like RAID-like setup, but there are, as I mentioned, setups where you protect the memory regions from other processes, or you don't on purpose, or you directly access it, or you access it through another path. So it has, or it utilizes the huge pages, or utilizes other things. So I can't name it right from the top of my head. I would have to look at the source code of the memkind library directly to the header file.
Interesting. And it probably works well in containers, so because they're transparent for what code to execute.
It's basically just a mount point. If you're using in the app direct mode, which means that your application has to be aware, it's a mount point on the file system. So if you use it with Docker or in cloud or Kubernetes, whatever, that should not be a problem. Hazelcast is cloud native, so I mean, whatever it means, but it works very nice with containers. So I don't like these buzzwords, but anyway, it works seamlessly in Docker, in containers, whatever.
Interesting questions. Virtual machines. I don't know if anybody uses them still, but if your CPU is virtualized, will the appropriate flash instructions be available? Probably yes, as you can work with general
That,
memory and if you're distant. It should be fine, but
yeah,
I'm not sure about kernel
I
support.
the kernel
games.
support for instance, one of the newest hottest memory mode in the persistent memory modules is the so-called KMM DEX, KMM direct access, when you really go directly to the memory, and this requires support from Linux kernels 5.1 and later versions. So you actually can't do it with any kernel, but this is the mode that we are actually moving to, because it provides even more. It provides direct access, so the other process can use the files or the memory that or read the memory. It's not locked. It's kind of unlocked. So there are some interesting things that can be tweaked with Optane memory or the persistent memory modules. Yeah.
So on one of your slides, you showed that crazy, marketing pyramid of Optane brand. So about the whole picture, Obtain Ssd, for as far as I know, deliver 4 to 10 times higher IOPS or lower latency than other high-end NVMe SSDs with regular NAND flash. And and since Intel Optane SSDs cost about 5 times as much as those flash NVMe devices per gigabyte of storage, architects of software system have to choose between a relatively little bit of lightning fast Optane or 5 times as much pretty darn fast NVMe flash. And now we have a new tier that is Optane persistent memory, which is 10 times as expensive and requires additional expensive infrastructure. For example, Xeon servers with Xeon motherboards, etc., and maybe even data centers specifically engineered for this. And now here we go again with performance to cost ratio. Is it worth in terms of money in the big picture of things where we have relatively slow but very, very cheap SSD devices?
I see. From our point of view, and the Hazelcast, we can't. The SSDs are pretty much out of the question because these are just slow. We are distributed cache. We are in memory. So anything basically slower than memory, much slower than memory, is already too slow, and we can't use it. Because we are talking about millions of operations per second. That's what our software can do pretty easily in the cluster. With all the fault tolerance, all the coordination mechanism and stuff. So spilling it on the disk or manipulating it on the disk with the data, that would kill the performance completely. So I'm not saying that the Optane persistent memory modules are for everybody. It's for certain workloads where you really need to, you go into sub-second latencies pretty much. I would qualify it as that. If you want to, or even like microsecond. If you go sub-millisecond, you probably already in memory, or should be. And if you and there it becomes interesting. But if your query takes 3 seconds, don't bother with Optane. That's a clear conclusion, I think.
Okay.
It won't save your ass magically.
How does the switcher combines with some network speed technologies like InfiniBand, or how was it called for Intel?
InfiniBand. We did some experiment at InfiniBand a long time ago. I don't know. We have never tried it combined together. That's the problem that we're having, or not having, but the very common use case with our customers is that they don't have special network cards. They don't have special network equipment like InfiniBand or super fast solar flare, network cards, 50 gigabits. If they have like 10 gigabits, 20, 40, that's like the top that we usually get. But so we haven't considered the Optane and the InfiniBand or these fancy network stacks together, because there's just no requirement at this point.
Okay.
Is it possible to share that memory between boxes, between servers? I mean, probably not now, but in theory, can we build an architecture that will share persistent memory between the servers directly?
Directly. Well, since it goes, since sits on the memory bus, right? So you have to go. You maybe can somehow, but it will kill the performance for sure. But that's an interesting idea. Maybe some kind of remote NUMA. I think there is some kind of technology that creates NUMA architecture even through several boxes for several machines. But this is I'm probably not the right person to answer that one, because I don't have a hands-on experience. I remember something reading about it, but no details.
Okay,
but
anyway.
I see where you're going.
Thank you. We can continue in Zoom in discussion zone. Jiří, thank you very, very much. That was interesting and fulfilled with detailed talk and a great discussion. It was nice to meet you.
Thank you very much, guys, for a lot of questions. Thank you.